All right, let's unpack this. We are diving into a subject that, most people probably overlook, yet it is absolutely central to modern infrastructure. I'm talking about the self-drilling screw, which is ubiquitously known in the industry by its trade name, the TEK screw.
Right.
This isn't just a piece of hardware. It's a tiny marvel of specialized engineering that quietly, accelerated the pace of construction globally.
It truly is the unseen hero. What makes the self-drilling screw so revolutionary is its incredible efficiency. It's an engineered solution designed to consolidate what were traditionally three distinct sequential steps.
Drilling, tapping, and fastening.
Exactly. Drilling a pilot hole, tapping the thread, and then finally fastening the material. It combines all of that into one single fluid motion.
It's a time saver that has to be measured in what, billions of labor hours?
Easily. It's staggering when you think about the scale.
So that's our mission today. An ultimate analysis for you, the learner, who wants to understand not just how to use this fastener, but the deep engineering and the global standards behind it. We need to cover everything from the core definition and its specific applications to decoding those highly critical European DEIN standards, the 7504 family.
All right.
And we need to get into the weeds of why some of these screws are paired with EPDM washers for long-term environmental protection.
We've got a comprehensive stack of sources here that really demands a thorough explanation. We have to dissect the screw's anatomy, explaining why its tip is built to cut steel, why its core resists snapping.
And how those global standards regulate its geometry.
Exactly. Our job is to bridge that gap from just a simple fastener description to a detailed understanding of why its material science is, frankly, a triumph of engineering trade-offs.
Okay, so the starting point for this deep dive has to be clearing up a massive point of confusion. It's one that trips up people from, novice DIRs all the way up to seasoned site managers.
I know exactly where you're going with this.
We have to clearly establish the difference between self-tapping and self-drilling screws. The industry maxim is simple, right? All self-drilling screws are self-tapping, but not all self-tapping screws are self-drilling.
That maxim perfectly encapsulates the functional relationship between the two. The distinction, really, it boils down entirely to one crucial step: the need for a separate pilot hole.
Okay, so let's look at the foundational concept first. The self-tapping screw. If a screw is designed to tap its own threads, why is a pilot hole so often required? Doesn't that sort of negate half the efficiency benefit if you still have to drill first?
That's an excellent question. The self-tapping screw does create its own thread profile as it is driven into a material, but its ability to drill the initial hole is severely limited, or in many cases non-existent.
So it's designed for softer materials.
It's designed to penetrate materials that are softer or have already been prepared, like thin-gauge sheet metal, plastics, or wood composites.
Yeah.
In any substantial material, even something like aluminum, you need that pre-drilled pilot hole.
Why, though? What does the pilot hole do?
It ensures alignment, for one. It also reduces material splitting, and it helps control the fit. Without it, you risk deforming the material or worse, snapping the screw because the torque required is just too high.
So the creation of the mating thread is integral, but the drilling remains a preparatory step.
Exactly. And within that self-tapping category, our sources detail two distinct mechanical actions based on the tip design. The first one is thread cutting.
Thread cutting.
These screws have a very sharp, often very defined cutting point. Crucially, they usually feature a flute or a notch cut into the laid threads right near the tip.
Like a channel. What's the purpose of that channel?
It acts like the flute on a miniature tap or a drill bit. As the thread cuts into the material, that flute performs two really vital functions.
Okay.
First, it actively cuts away material, creating a cleaner thread profile. And second, and this is perhaps more important, it provides a channel for the chips, the debris, to escape.
So it clears its own path.
It prevents the screw from jamming or binding, which makes them ideal for materials where chip clearance is necessary. Think harder plastics or, denser but still thin sheet metal alloys.
That makes perfect sense. Managing the debris is key. Okay, so what's the second type?
That would be thread-forming screws. These often have a much blunter or more tapered point, and they don't have those aggressive cutting flutes. Their mechanism is fundamentally different.
How so?
Instead of removing material, they displace it. They essentially cold form the material around them, pushing it aside to shape the thread.
Pushing the material instead of cutting it. What's the advantage of that method?
By displacing the material, thread-forming screws achieve maximum thread engagement. The material is compressed, which leads to a much stronger and often tighter fit in that pre-drilled hole.
So it's a stronger connection.
Much stronger. They're commonly used in situations where you want high resistance to vibration loosening, because the formed threads are essentially stress-hardened material that's been molded perfectly to the screw profile.
But I'm guessing there's a trade-off.
Oh, absolutely. This process requires significantly more torque to drive the screw than thread cutting does.
Okay, now let's transition to the real innovation. The self-drilling screw, the TEK screw. This is where the pilot hole preparation is completely eliminated.
Yes, the moment we attach that drill bit tip to the screw shank, we cross the boundary into self-drilling technology. The tip of a TEK screw is engineered specifically to function as a high-speed drill bit. It's doing 3 actions in sequence, but they feel simultaneous to you, the user.
Right.
The tip first drills a precise, perfectly sized pilot hole. Immediately following that, the threads tap into the fresh material, and finally the fastener pulls the materials together and secures them.
In one motion.
One smooth, continuous motion. This one-step action is the fundamental reason for their dominance in sheet metal and light structural steel assembly.
That drill tip is really the star of the show then. And our sources emphasize that its capability is standardized through the TEK point numbering system.
This numbering system is absolutely crucial for proper specification. It runs from typically number 1 to number 5, though you can find specialized applications that push it up to number 7.
And a higher number doesn't just mean a better screw, right?
Not at all. It means a longer, more complex, and more robust drill point that's designed to handle thicker or harder substrates.
So if I'm a user on a job site, how do I determine if I need a number 2 point versus, say, a number 5 point?
It's dictated by the total thickness of the material being drilled, especially the thickest material you are penetrating. A number 1 or a number 2 point is typically sufficient for thin gauge sheet metal, maybe up to, an eighth of an inch total thickness.
Okay.
When you move up to a number 5, you're looking at penetrating structural steel purlins that can be half an inch thick or even more.
And what's the mechanical necessity behind that length requirement? Why does it matter so much?
It's all about preventing binding, which, as we noted, leads to immediate failure. The rule is technical, but it's completely non-negotiable. The unthreaded pilot section of the drill tip must be long enough to completely drill through all layers of the material being joined before the first load-bearing thread starts to engage that material.
So if the thread engages while the drill tip is still trying to get through the material, everything just seizes up.
Precisely. If the thread starts grabbing the material while the tip is still cutting, the screw attempts to pull the material up against the head before the hole is fully clear. This generates immense friction and axial load, causing the screw to bind. The torque required skyrockets, often leading to tool burnout, stripping the fastener head.
Or worst of all, just snapping the screw shank right off.
Exactly. Specifying the correct point number ensures the hole is finished and the metal chips are cleared before the threading action even begins.
That brings us to the practical trade-offs for the person who's actually driving these screws all day.
And the trade-offs are significant. Self-tapping screws, especially the thread-forming types, often require less sophisticated installation tools and they're cheaper to manufacture. The self-drilling TEK screw, while it offers unparalleled on-site efficiency and saves all that cost of pre-drilling labor, it demands professional-grade equipment. You need high-torque, variable speed drills, often impact drivers, capable of generating the high revolutions per minute necessary to cut steel effectively.
I can just imagine the frustration of someone trying to use a standard household drill on a thick steel frame.
It's a classic failure scenario. The friction generated by drilling hard steel creates intense heat. If the drill speed or the torque is insufficient, that heat builds up incredibly rapidly.
And the tip just gives out.
It causes the exquisitely hardened drill point to instantly lose its temper. It loses its hardness or burns out before it even penetrates the material. The tip simply turns blue, dulls, and stops cutting, rendering the entire screw completely useless.
So the TEK screw is really a system.
It is. Its efficiency relies equally on the screw's own engineering and the power of the tool that's driving it.
Okay, so this ability of the TEK screw to perform all these functions, you're saying it relies on solving a pretty profound metallurgical paradox.
It does. It has to be hard enough to slice through steel, but at the same time tough enough to handle the immense twisting force of installation without breaking.
A paradox indeed. Because hardness and toughness are generally, mutually exclusive properties in metallurgy. Hard materials tend to be brittle, and tough materials tend to be soft. So how do engineers achieve this impossible balance?
The solution is a really clever application of thermal processing. It's called differential heat treatment, or more commonly, case hardening.
Right.
We don't make the entire screw one uniform material. We engineer different properties into the core and the surface.
Let's break down that process. What kind of material are they even starting with?
We typically start with low or medium carbon steel alloys, something like a C1022 or a C10B21. These materials are inherently ductile and they're easy to cold form. The differential treatment involves a multi-step process beginning with carburization.
Rubberization.
Yeah, that means heating the screw in a carbon-rich atmosphere. This causes carbon atoms to diffuse into the surface layer, enriching it significantly.
So you're kind of like coating a soft chocolate bar with a thin, hard candy shell.
That's a perfect analogy. We are intentionally making the surface structure fundamentally different from the interior. After carburization, the screw is quenched, rapidly cooled, and then it's tempered. This process precisely controls the microstructure.
And this results in the dual profile.
Exactly. The surface layer, or the case, has extremely high hardness. We're talking levels often exceeding 50 on the Rockwell C scale, or HRC, or over 590 on the Vickers scale. This extreme hardness allows the drill point and the initial threads to cut even high-strength structural steel.
And the core remains tough to handle the load.
Precisely. The interior core of the screw, which didn't absorb as much carbon during carburization, remains comparatively softer and significantly more ductile, typically in the HRC 2834 range.
And that's what keeps it from snapping.
That toughness allows the screw shank to withstand the immense torsional stress generated when driving a fastener through thick steel. The core acts like a piece of taffy. It can twist and flex without snapping, preventing that catastrophic shearing failure under high torque.
Because if the whole screw were 50 HRC,
It would be far too brittle. It would snap the moment it encountered any real resistance.
the choice of base material, you mentioned C2022 versus C10B21, that's also fascinating. Our sources highlight the role of boron in C10B21. It sounds like such a small detail, but it makes a huge difference.
It's the micro-alloying effect at its absolute best. C2022 is the standard workhorse. It's reliable and economical. C10B21, however, contains a trace, almost minuscule addition of boron.
And this is known as the boron effect.
Right, and its impact is disproportionately large. It dramatically enhances the steel's hardenability.
How does that actually work in practice? What is hardenability?
Boron affects the microstructure during the quenching phase. Steel needs to cool at a certain rate to form the hard crystal structure known as martensite. Boron acts as a kind of barrier, slowing down the competing thaw-after transformation phases like ferrite and pearlite.
So it helps the steel become harder more easily.
It means that even with a slower, less aggressive quench, C10B21 can achieve a deeper and more uniform hardening depth than C2022 can.
Why does the user care about a slower quench and deeper hardness? What's the practical benefit?
The deeper and more predictable hardness allows C10B21 to reliably achieve significantly higher core strengths, things like the demanding structural benchmark of property class 8.8.
Which is comparable to what?
It's comparable to high-end, much more expensive alloy steels. So for the structural engineer, this means they can use an economical carbon steel TEK screw in applications requiring high tensile strength and shear loads, trusting that the core will resist failure even when penetrating challenging structural members. It just elevates the performance ceiling of the entire fastener line.
Let's shift our focus now from the metallurgy of the core to the critical geometry of the outside, the drive type and the threads, starting with the drive interface.
The drive system is where the energy transfer happens, and it's a critical factor in installation efficiency and, frankly, safety. For larger, heavier-duty TEK screws, especially those adhering to the DIN 7504K standard, the hex drive is traditional and standard. It's built to handle maximum torque transfer.
But if you spend any time on a construction site today, you'll see a massive migration toward Torx, or six-lobe drives.
Oh, absolutely.
I personally love the Torx system, and I think everyone who has ever stripped a standard Phillips head in a moment of high tension understands exactly why.
You're hitting on the core advantage. Torx offers dramatically superior torque transfer because the driving forces are applied radially against the walls of the recess, not just pushing down into a slot or cross.
And that design virtually eliminates cam out.
It does. That infuriating moment when the bit slips out of the head under high load, cam-up strips the fastener head, it damages the bit, and more importantly, it can injure the installer. This improved efficiency and safety is why Torx is so rapidly becoming the standard for higher-end fasteners, even if the tools are slightly more specialized.
Okay, moving to the head itself, we have pan, truss, and hex washer. These aren't just cosmetic choices, are they?
Far from it. The head types are specifically engineered to manage load distribution and prevent pull-through, which is where the joined material fails around the fastener head.
So the head shape matters for strength.
Immensely. The hex washer head, which is common in structural applications, provides that large bearing surface. It maximizes the clamping area to distribute the load across thin-gauge materials like steel sheeting. A truss head, which is even wider and flatter than a pan head, is designed for similar reasons, like when you're fastening wood or plasterboard to metal studs. It ensures the soft material isn't easily crushed or pulled through.
Finally, let's detail how the threads are formed, which, like the core hardness, is crucial for long-term reliability.
Most high-performance TEK screws are manufactured using thread rolling, not thread cutting.
Thread rolling.
It's a cold-forming process where hardened steel dies press the thread profile onto the round shank of the screw. It is a formative, chipless process. It displaces the metal rather than removing it.
And why is displacement better than cutting when it comes to strength?
The key is what happens to the metal's internal structure. It's grain flow. When you cut a thread, say on a lathe, you actually sever the metal's grain structure at the roots of the threads.
And those become weak points.
They become stress concentration zones, making them highly vulnerable to crack initiation and fatigue failure. Thread rolling, however, displaces the material, forcing the metal's grain flow to remain continuous, following the contour of the thread smoothly.
Can you give us an analogy for that?
Imagine the metal grain like the fibers in wood. If you cut across the fibers, the wood is weak. If you bend the fibers, the structure remains strong. That uninterrupted grain flow achieved through rolling is paramount for enhancing the fastener's resistance to fatigue under cyclic loading.
So things like wind, vibration, temperature changes.
Exactly. If the structure it holds is subject to any of that, a rolled thread is far, far less likely to fail than a cut thread. It's a non-negotiable step for high-performance structural fasteners.
Okay, now we enter the world of regulation and standardization. For anyone specifying or importing these fasteners in Europe, you quickly run into the German DIN 7504 family. So why do we need these standards, and what do the suffixes K, N, and P tell the user about the screw's intended purpose?
Well, standards are the universal language of engineering. They ensure that a screw manufactured in Italy performs identically to one made in Germany, guaranteeing reliability, interoperability, and of course, safety. For self-drilling screws, GIN 7 and 504 has defined the geometry, strength, and performance requirements for decades, even as it has been officially superseded by the harmonized ISO standards.
So understanding the DIN letter suffix is the quickest way to identify the screw's head style and its primary use case.
That's the shortcut, yes.
Okay, let's start with DIN 7504K, which I understand is the most commonly used structural type.
DIN 7504K, which is now largely governed by ISO 15480, is the undisputed hex head workhorse. The K historically refers to the hexagon head form, specifically designed with an integral washer face. This head is built for maximum clamping force and load distribution.
And where do we find the K workhorse in action?
Its primary domain is heavy-duty exterior fastening, so roofing, metal cladding, and structural steel-to-steel connections. Think about fixing a large profiled steel sheet onto a steel purlin high on a warehouse roof. The K screw, particularly when it's paired with a bonded washer, is mandatory here. The large hexagon head allows for extremely high torque application, which is necessary for the high point number required to penetrate thick steel, and the broad washer face helps distribute the considerable forces generated by, say, wind-up lift and thermal expansion across the sheet metal panel.
So the choice here is critical for structural integrity against high lateral loads.
Absolutely.
Okay, that brings us to DIN 7504N, the versatile choice.
That's DIN 7504N, corresponding to ISO 15481. The N denotes the pan head, which is characterized by its rounded top and flat bearing surface. The primary characteristic of the N screw is its versatility and its relatively low profile.
Where is its application strength? Where does it shine?
It excels in general purpose, metal-to-metal assembly, especially where heavy clamping force isn't the primary requirement, but a tight, low-profile connection is needed. You find the N screw everywhere.
Like
assembling HVAC ducting systems, electrical enclosures, machinery panels, light-duty fabrication. Because of its smoother, rounded top, it's often preferred in interior machinery or electronic assemblies where sharp edges have to be avoided and clearance is a consideration. It's really the fastener of choice when robustness and aesthetics are equally important for interior-facing panels.
And finally, the specialist for clean, flush finishes, DIN 7504P.
That is DIN 7504P, which is aligned with ISO 15082. The P signifies the countersunk head, meaning it has that distinct conical shape designed to seat perfectly flush or even slightly below the surface of the material when it's installed in a pre-punched or countersunk hole.
And beyond just pure aesthetics, why is a flush finish so critical in some applications?
It often moves beyond mere appearance and into functional and safety territory. In specialized facade installations, for instance, a protruding head can interfere with adjacent panels or sealants, which can compromise the entire weather barrier.
Ah,
And in environments requiring clean lines like food processing equipment, passenger vehicle interiors, or high-speed machinery, a flush head prevents snagging, makes cleaning easier, and can even contribute to smoother airflow or reduced noise generation. We actually found a case study of a specialized London architectural installation where they used thousands of 7,500 four-piece screws, not just for the visual continuity of the metal facade,
but for a mechanical reason.
but because the flush design contributed significantly to preventing shear stress concentration points and ensuring the facade met specific wind load requirements without any unsightly deformation. It was a mechanical requirement masked as an aesthetic one.
It's clear these standards are far more than just descriptive labels. They are prescriptive engineering requirements. You mentioned the shift from DIN to ISO. What's the practical implication of that for the European market, particularly when it comes to construction?
The transition is mandatory under the European Construction Products Regulation, or CPR, and this is where the standard moves from a recommendation to a legal requirement.
So it's not optional.
Not at all. If a self-drilling screw is to be used in a structural application within the EU, a roof, a building facade, any load-bearing element, it must carry the CE marking. And to earn that CE mark, the manufacturer often needs what's called the European Technical Assessment, or ETA.
And the ETA is crucial.
It is. It's a technical specification that goes far beyond just the DN geometry. It tests and verifies the product's performance characteristics, things like its shear strength, its pull-out resistance, resistance to vibration, and its durability under specific environmental conditions. It proves the screw is fit for its intended structural use and often specifies the exact number of decades the product is expected to last without failure.
So compliance is not optional. It's the price of market entry and liability protection.
Exactly.
So if a contractor uses an imported screw labeled only at DN TATI 504K, but it doesn't have the associated CE mark and ETA, they are potentially using a non-compliant product, even if the geometry looks correct to the eye.
Precisely. The older DI numbers remain a useful shorthand for geometry, but the actual technical and regulatory substance lies in the ISO harmonization and the required CPR compliance testing. It guarantees the end user, you, the customer, that the strength and longevity promised by the material science we just talked about are reliably delivered.
Okay, so when we install that DIM 7504K hex head screw onto a metal roof or a cladding panel, we immediately create the greatest single vulnerability in the entire structure.
A whole.
A hole. For exterior construction, the most common mode of failure isn't the screw snapping, it's water ingress, which leads to rust, degradation of insulation, and eventually structural decay.
Which is why the humble, often overlooked bonded washer is absolutely critical.
It seems like a simple rubber gasket, but your emphasis suggests it's far more specialized than that. What makes this EPDM washer such a vital piece of the system?
Well, it is an engineered sealing system designed for structural longevity. It's usually composed of a layer of EPDM, that's ethylene propylene diene monomer synthetic rubber, that's securely bonded to a metal backing, often galvanized or stainless steel. This combination ensures the seal is robust both mechanically and chemically.
Why EPDM specifically, though? Why not standard rubber or silicone?
EPDM is chosen for its exceptional environmental resilience. Standard natural rubber degrades very quickly outdoors because it's highly susceptible to UV radiation, ozone, and wide temperature variations. EPDM, being a synthetic thermoset elastomer, incorporates diene monomers which allow for strong cross-linking during vulcanization. This resulting chemical structure gives it superb resistance to atmospheric degradation.
And our sources highlight its incredible operating range.
It's amazing. It maintains flexibility and sealing capability in temperatures ranging from approximately minus 50 degrees Celsius to well over plus 150 Celsius.
So what does that mean in real-world terms?
It means the washer will not harden, crack, or dry out processes, known as embrittlement, over decades of exposure to harsh sun and temperature cycling. And that is the primary failure mechanism for lower quality sealing materials.
So when the screw is driven, how does the EPDM actually create the waterproof seal?
As the screw tightens, the metal backing plate compresses the EPDM rubber against the surface of the sheet metal panel. Because EPDM is so flexible and elastic, it conforms precisely to the microcontours and any minor inconsistencies of the panel surface.
It fills in all the little gaps.
It effectively fills the small gap between the screw head and the sheet, creating a durable, long-lasting, watertight barrier that completely seals the drilled hole against rain, snow, and any wind-driven moisture.
That makes the installation technique non-negotiable then. I imagine having the best material in the world doesn't matter if it's driven incorrectly. What's the classic failure scenario during installation?
Proper compression is absolutely everything. The ideal seal is achieved when the washer is compressed just enough to form a slight, visible mushroom shape, where the rubber flares gently out from under the metal backing.
A mushroom shape. Okay.
This indicates a firm, even contact pressure.
So what happens when the installer just relies on brute force?
Over-tightening is the construction site horror story. If you apply too much torque, two things can happen. First, you can crush the EPDM out from under the metal backing, essentially deforming the rubber beyond its elastic limit, which compromises the material integrity and can even split it.
I see.
Second, excessive tightening can buckle or dimple the metal panel itself, which also destroys the flat surface you need for a seal. In either case, a crushed, split, or extruded washer, you have an immediate, guaranteed path for water ingress,
And that failure often requires costly replacement.
sometimes leading to structural repairs down the line, all because of a fractional second of excessive torque. Many professional roofing crews use specialized clutch-equipped screw guns to deliver precisely the specified torque and achieve that perfect mushroom profile every single time.
Okay, moving from water sealing to the structural material itself. Since TEK screws are so often outside, we must address corrosion. This is where the different grades of stainless steel come into play, defined by their chemical structure and alloying elements like nickel and molybdenum.
Absolutely. And the choice of stainless steel is an environmental decision, often guided by ISO classifications from C1, which is dry interior, all the way up to C5, which is severe industrial or marine.
So we need high strength for the drilling tip, but extreme corrosion resistance for longevity.
Which pits three key stainless types against each other. First, we have the high-strength option that requires heat treatment, martensitic stainless steel. That's something like grade 410 or C1 in the fastener codes. This grade has minimal nickel, so it's relatively inexpensive.
And the crucial point is its ability to be fully hardened.
Exactly. It can be hardened by quenching and tempering to achieve that high HRC 50+ case hardness we discussed earlier. Because it can be hardened, it's often used for self-drilling screws. However, its corrosion resistance is limited, making it typically suitable only for dry interior or maybe mildly controlled environments.
So good strength, but not for the coast. Then we move into the truly corrosion-resistant grades.
That takes us to austenitic stainless steel grade 304, or A2. This is the general-purpose, cost-effective corrosion workhorse. It contains significant nickel, typically 8% to 10.5%, which stabilizes its structure and provides excellent general corrosion resistance. It's also highly ductile.
But I read that 304 cannot be heat-treated to gain strength.
That's right. Austenitic seals cannot be hardened through quenching and tempering. Their strength comes primarily from work hardening during the thread rolling and cold forming processes.
And what's the major limitation of 304?
Its Achilles heel is its susceptibility to corrosion in chloride-rich environments.
So salt water.
Coastal areas, near swimming pools, or where de-icing salts are used extensively. The chlorides can break down the passive oxide layer on the steel, leading to localized attack called pitting and crevice corrosion.
Which brings us to the ultimate grade, the marine standard.
That would be austenitic stainless steel grade 316, or A4, which commands a premium price point. Grade 316 includes both nickel and a critical alloying element, molybdenum, typically added at 2% to 3%. Molybdenum fundamentally alters the way the passive layer interacts with aggressive compounds like chlorides. It significantly increases resistance to pitting and crevice corrosion, which are the main modes of failure in salty or acidic conditions.
So this is the choice for the harshest environments.
It is the absolute requirement for severe industrial, chemical processing, and marine applications. It's the go-to fastener for ISO C5 corrosive environments. It offers a vastly extended service life where 304 would fail prematurely.
It's fascinating that despite the strength and corrosion resistance of stainless steel, standard carbon steel TEK screws are still used in demanding environments through the application of advanced coatings.
That is a huge area of modern innovation. When you can't afford grade 316 or when you need the sheer mechanical strengths, that property class 8.8 that is easier to achieve in carbon steel alloys like C10B21, you have to rely on coatings.
Standard zinc plating isn't enough for that.
Standard zinc plating is fine for C1, maybe C2 environments, but for demanding outdoor C3 or C4 conditions, you need multi-layer protection.
And the example our sources provide is rustburt.
Rustburt is an excellent example of a multi-layer hybrid system that's engineered for superior performance and abrasion resistance. It's a three-layer process. A metallic zinc-based layer provides sacrificial galvanic protection. A chemical conversion film acts as an intermediate barrier, and crucially, a high-performance ceramic top coat is applied.
Why is that ceramic top coat so vital?
Because the biggest risk to a coated fastener happens during installation. Fasteners are scraped, dragged across rough materials, hit by tools. The high-performance steel TEK screws need a coating that resists mechanical damage.
And the ceramic provides that.
The ceramic top coat provides that superior abrasion and scratch resistance, ensuring the underlying zinc and chemical protection layers remain intact. If you scratch a standard zinc coating down to the steel, corrosion starts instantly. The ceramic layer maintains the physical barrier, extending the screw's lifetime dramatically, often achieving 1,000 hours or more in salt spray testing. And, what's more, the entire rustburt process is cured at a low temperature, typically below 200 degrees Celsius.
And that's important because
It's key because if the coating process required high heat, it would compromise the careful differential heat treatment, that hard case and ductile core we achieved earlier. It would effectively ruin the screw's mechanical properties. Low temperature curing preserves the integrity of the C10B21 core strength.
So let's bring this full circle for the learner. What began as a simple request to understand the TEK screw has really revealed a complex, meticulously engineered system. The screw's efficiency comes from that complex dual hardness profile, a hardened case for cutting and a ductile core for torsional toughness.
Right.
We've learned that its application is defined by the strict DIN 7504 standards K for structural roofing, N for general assembly, P for flush finishes. And finally, that the EPDM washer is not an accessory, but a high-performance weather sealing device designed to last decades in harsh environments.
And the primary lesson here, I think, is the economic reality of fastener choice, which is encapsulated by a concept of total cost of ownership, or TCO. The decision to select a specific fastener is never just about the initial unit price. The highest initial cost, such as the premium for a grade 316 stainless steel screw, is almost always easily justified if it prevents premature failure.
Right. The cost of failure is always higher.
The non-monetary costs of failure, including structural remediation, replacement labor, downtime, or even litigation due to a failed weather seal, always eclipse the small initial savings made by using an inferior fastener.
It's the difference between investing for 50 years versus just buying for this afternoon.
Precisely. Underspecifying is a massive technical and financial risk, which leads to a high TCO. Overspecifying is simply wasteful. The most effective engineer chooses the fastener that reliably meets the required design life at the most economical initial price point, balancing high strength like C10B21 with rustburt against ultimate corrosion resistance like grade 316.
That's a perfect encapsulation of engineering economics. Now for our final provocative thought, we've analyzed how the TEK screw revolutionized installation efficiency, but the economic landscape is rapidly shifting. In Europe, a new geopolitical and climate policy is adding a completely new layer of cost. The Carbon Border Adjustment Mechanism, or CBAM.
CBAM, in simple terms, is a carbon tariff. It's imposed on imports of carbon-intensive goods, and steel fasteners fall directly into its scope. It's designed to prevent carbon leakage, which is when companies relocate production to countries with weaker climate policies, and it forces importers to account for and purchase certificates corresponding to the carbon emissions embedded in the product during its manufacturing.
So for the first time, a screw's environmental footprint directly translates into its landed financial cost.
Absolutely. CBAM fundamentally links the embedded carbon emissions in imported steel fasteners to a financial cost, requiring sophisticated tracking and verification of a product's entire supply chain history. It elevates carbon emissions from a purely environmental concern to a primary factor in procurement and total cost.
Therefore, the ultimate question for the future of structural hardware, will the TEK screw of tomorrow be judged not just by its point hardness, its property class 8.8 rating, or its resistance to pitting and crevice corrosion, but by the measurable verified carbon emissions embedded in its steel? That means selecting a low-carbon C10B21 screw from a supplier using verifiable renewable energy could become a decisive strategic tool for global market competitiveness. It would transform the humble tech screw from a matter of mechanical engineering into a strategic component of global climate policy and trade compliance.
The cost of carbon is now the newest, most volatile variable in the fastener strength equation. That is certainly something worth mulling over.
Indeed, something to mull over until our next deep dive.